In this section, we get into rational exponents. A rational number involves division, so 3 over 7 is a rational number. A rational exponent is an exponent that's a fraction. So in the definition here, it says the number on the bottom is the root. If I write some number to the 1 over n power, this n on the bottom is the same index that goes here. So what that means is if I write something like x to the 1/3 power, x to the 1/3 power is the same thing as the cube root of x. You notice the numerator is 1 eventually, and it's going to take us a little time to get there, but eventually we'll get to what happens when that numerator is not 1. Right now, all we're focused on is that thing on the bottom. So the root is down the bottom. Some people say in a tree, roots grow down. Well, really in anything, roots grow down, I guess. But if you have x to the 1/3 power, that 3 is the root. So we can evaluate expressions that are written with rational exponents as well as roots. So here's a whole bunch of them. Let's work through a few of them. The first one says 36 to the 1/2. 36 to the 1/2 is the equivalent of the second root of 36. The second root is nothing weirder than just the square root. So the square root of 36, what number multiplied by itself twice will give you back 36? The answer is 6. Over here, 64 to the 1/3 says what number multiplied by itself 3 times will give me 64. So the third root of 64 is 4, because 4 times 4 times 4 will give me back 64. Now, look at that third one. That third one says -4 to the 1/2. Well, -4 to the 1/2 says what number times itself twice will give me -4, and there is none. Because the second root is the same thing as the square root, I can't take the square root of a negative number. It's not real. Here we're keeping it real, so I can't do that. All right, 8 to the 1/3. What number times itself 3 times will give me 8? It's 2. All right, that's the same thing as asking you for the cube root of 8. Over here, notice that there's a set of parentheses, negative on the outside, so I'm asking what number times itself 3 times will give you -8. The answer is -2, because -2 times -2 times -2 will give you -8. So you can take the third root of a negative number. You can't take the square root or the fourth root or anything like that. And then the last one, what number times itself twice gives you 100? It's got to be 10. For these numbers down the bottom, these are not perfect squares and perfect cubes. So this first one can be written as the square root of 29. Now, if somebody asks you for an approximation, you can grab a calculator, get an approximation. It's going to be something between 5 and 6, right? The square root of 25 is 5. Square root of 36 is 6. So somewhere in between there is the square root of 29. The same thing here, right? This is the equivalent of the cube root of 43. And so I know the cube root of 64 is 4. The cube root of 27 is 3. So 3 point something. All right, these questions say write using radical notation. Look to see where the parentheses are. Here the parentheses is around both the 6 and the x. So if it's to the 1/2 power, square root, 6x. Done. All right, this next one, cube root. Right, it's 3 down the bottom, so that 3 becomes my index. I get the cube root of 8x. Eventually, we'll simplify that, and we can make it the same thing as 2 times the cube root of x. But for now, I'm just going to write it in radical notation as the cube root of 8x. The same thing for the third one, right? This is to the 1/2 power. 1/2 power is square root. Square root of 9x to the 4th. And yeah, it turns out I can simplify a 9x to the 4th by writing it as the square root of 9, square root of x to the 4th. So square root of 9 is 3. Square root of x to the 4th is x squared. All right, for the ones on the bottom, it says write as a rational exponent. So we're going to take what's in that radical and we're going to turn it into a fraction. So 16x, there's a little 2 that's hiding over there. So it becomes 16x to the 1/2. Now you can take the square root of 16 and get 4 and write it as 4x to the 1/2. But you notice that I didn't put parentheses around the 4x. Because in the original radical expression, that 16 and the x are both under the square root. So when I write it as a power, 16x to the 1/2, both the 16 and the x are in that power. Once I evaluate 16 to the 1/2, 16 to the 1/2 is 4. The only thing that retains that exponent is the x. All right, for the next one, I can't really simplify it at all, so I'll just write it as 6x. What's my power? 1/3 power. Over here, my 9x squared, What do I do for a fifth root? Easy. Put it on the bottom of the fraction. 9x squared to the 1/5. And over here, this gives me an 8x squared. What's my power? It's third degree, so it goes underneath the fraction. Right? And yeah, I can simplify 8 to the 1/3 as 2 and get 2x squared to the 1/3 power, which actually I can write as 2x to the 2/3, but I think I'm getting a little ahead of myself, so we can leave the answer like that. All right, I promised we were going to get to what happens when the numerator is not 1, and, well, here we are already. If we have an nth root, the root goes down the bottom. What happens when we add an exponent? Well, the exponent goes up on the top. So the nth root of a base to a power, here's the root, there's the power. So in that last example, I was doing an x to the 2/3. I can take numbers raised to the 2/3 power. Suppose I took 8 to the 2/3 power. What this is saying is take 8 to the 1/3 power and then square it. So 8 to the 1/3 power is 2, and then 2 squared is 4. The equivalent radical expression would be the cube root of 8 squared. So do you see that that 3 that was on the bottom goes in the root position, the 2 that's on the top goes in the exponent position. And it turns out it doesn't matter what order I evaluate this in. 8 squared is 64, so I could have just as easily said, what's the cube root of 64? The cube root of 64 is 4. On the one I did on the top, I did the root first, and then squared it and got the same answer. Now this assumes that you're putting those fractions that are in the exponent spot in simplest terms, and it has to do with negatives, and it does get a little bit nitpicky, but the reason is basically this. Suppose I said I want to evaluate -8 to the 1/3. I can evaluate -8 to the 1/3, and I'll get -2, because -2 times -2 times -2 gives me back -8. If I said I want to evaluate -8 to the 2/6 power, one way that will work and the other way it will not. I can take -8 squared and then take the 6th root, and I'll be fine. But I won't get the same answer as I got in the first place, right? -8 squared is 64. The 6th root of 64 is +2. The other way of doing this doesn't exist. If I say I want to take the 6th root of -8 first, I can't do that because it's not real. So whichever way I operate this, I should get the same answer. And if I don't simplify that expression in the exponent spot first, then I'm either going to get a different answer or no answer at all. So we simplify the fractions first, and then we evaluate them. And that's why I said roots and powers can be done in either order. I showed you that up on the top. Oftentimes we take the roots first simply because it makes the number smaller. So let's try a couple of these. 64 to the 2/3 power. So this is the same thing as saying take the cube root of 64 squared. I would like to take the cube root of 64 first because I don't know what 64 squared is off the top of my head. But I do know that if I take the cube root of 64, I get 4, and then I square it, and I get 16. Right? So cube root first, then we square. Let's try the same thing over here, right? This is the identical expression of saying take the cube root of 27 and raise it to the 4th power, or take 27 to the 1/3 and raise it to the 4th power. Both of these are just different representations for the same thing. So the cube root of 27 is 3. Raise 3 to the 4th power. 3 times 3 is 9. 9 times 9 is 81. Right? So that's 3 times 3 times 3 times 3. For the third one, take -8 to the 1/3 power, and then raise that to the 5th. So the cube root of -8 is -2. -2 to the 5th, 2 times 2 times 2 times 2 times 2, 32, and we know it's going to be negative. Right, so we can do the root first and then the power. Makes the number smaller. You could do it the other way. You're welcome to do -8 to the 5th. I do not know that off the top of my head. And if I can do this without a calculator, it makes it easier. All right, this last one was the little example I was giving you before. You notice the issue is that this 8/6 is not simplified. So if I simplify that 8/6, take a 2 out of the top, take a 2 out of the bottom, oh look, I have a very similar problem to what I had before. Now I can take the cube root of negative 27 and get negative 3, raise negative 3 to the fourth power, and I get a positive 81. If I had taken negative 27 to the fourth, clearly that would give me a positive number. The cube root of that would be 81. The second set of problems says if you can't evaluate by hand, leave the answer as a radical. So look at 10 to the 3/4. I can't take the fourth root of 10, can I? Can I take 10 to the third? Yeah, I got 1,000, but what's the fourth root of 1,000? I don't know. So I'll take the fourth root of 10 cubed, which I could also write 10 squared is 100, 10 to the third is 1,000. Leave it like that. All right, over here, I can write this as the fourth root of 16x squared. I do know that the fourth root of 16 is 2, and I can pull that out of the radical, but what's left then is just the fourth root of x squared. And as the chapter goes on, we'll get into simplifying these a little bit more. So I could leave it as the fourth root of x squared. All right, 81 to the 3/4 power is asking me to evaluate 81 to the 1/4 and then cube it. Does this come out as anything? 3 times 3 is 9, times 3 is 27, times 3 is 84. Oh, so this is inside is 3 to the third gives me 27. So that one comes out just fine. This last one will not. Right? If I take the fifth root of 14 to the fourth, I can just leave it like that. Right, as we go through this, we realize that the rules that applied before to things like negative exponents apply now as well. So let's split this up, make a second video with negative exponents and applications.